Hi. So my name is Ueyama. I'm a software engineer at Google, and I'm working on LLVM linker, LLD, for a few years now. And then I'm going to give you a presentation about the linker. So this is an overview of my talk. So if you guys have subscribed to LLVM developers mailing list, then you may be seeing a lot of activities going on for LLD, and you may be wondering what's the status of the project and how usable it is, or what's the reason to create a new linker and switch to the new linker. And I want to answer to these questions. And after that, I'm going into some technical details of the linker to give you an insight that why LLD is better than other linkers. I also want to mention that the differences in semantics in the linker, and I'm going to cover other stuff. So LLD is actually basically 3 different linkers in a single binary. So I have to talk about each port. So ELF port, which is for Unix, is pretty much production ready. I know a few big companies that are using LLD as their internal linker, and we are switching Chrome to link LLD as a linker, and FreeBSD is actually switching to LLD entirely, so that user being LD in the upcoming version of FreeBSD, at least for AMD 64 architecture, is going to be LLD, which means a lot, because that means LLD can link everything on the system, right? Including all user and programs, as well as kernel. So that means a lot. So speaking of COFF, which is for Windows, that is pretty much complete now too. Including debug info support, which is awesome, because you can debug stuff linked with LLD using Visual Studio, because it's actually compatible debug info, and LLD is 2 times faster than Microsoft linker. So and it takes the same command line options as Microsoft linker, so you can just use LLD to get everything plus speed, which is awesome. And Mach-O is not finished. And I'll be focusing mainly on ELF port of the ELF port in this slide, but the same thing is also applicable to COFF, because in COFF and ELF we share the same design and some code. So when we restarted the project, we set out these goals. So first thing I wanted to achieve is to make it simple, and I think that we achieved that goal, because LLD is much simpler than GNU linkers in many metrics, and by making it simple, it is pretty much hackable, I would say. So it is easy to add new features, or easy to add experiment your new ideas based on top of the linker, and which is a good thing. And also, it has to be fast, right? Because as long as linker works correctly, do you really care about the features that the linker has? Probably no. As long as it runs correctly, then the only thing you care is probably speed. And LLD does a great job at that. I'll speak about that later. And it also has to be easy to use, easy to switch. And actually, LLD for ELF takes the same command line arguments as GNU linkers do. So you can just replace the linker. And the same is true for COFF. So if you want to use LLD, then if you are brave enough, then you can just replace the system linker with LLD. Or if you don't want to do that, then you can pass a parameter to Clang to use an alternative linker. So here's the fun part. But before getting into the details, I have to describe the situation of GNU linkers because there are two GNU linkers, so it's plural. And the reason is being that, so there was only one linker in BUtils, which is so-called BFD linker. And that was a very old program, and it got LF support almost 25 years ago. And then at that time, the average size of executable is very small, right? Like dozens of kilobytes or maybe smaller than that. But it didn't scale well, so they decided to create a new linker from scratch for ELF, and that landed as a gold. But gold cannot really replace BFD linker because BFD linker supports other architectures and other targets than ELF only gold. So they still keep two linkers in their distribution. So naturally, if you wanna make LLD faster, then the target would be gold because it's a faster replacement. And LLD is actually 2 to 4 times faster than gold on average. And if you link the small program, like something that you can link within a second, then you cannot really see a big difference, but it doesn't really matter. And if you link a large program, something like it takes 30 seconds or a few minutes, then you can really see a significant difference. And I think this is the takeaway of my slide. So this is a time to link programs. So shorter is better. And it seems too good to be true, but it is actually true. and if you, so except the Linux kernel, LLD is 2 to actually 5 times faster than gold in these test cases. So for example, Clang with debug info takes 33 seconds to link with gold, but LLD can do that only in 5 point some seconds, which is not 4 but 5 times faster. And if you add BFD linkers numbers, then graph becomes like this. And this is why I didn't include these numbers in the previous chart, because it makes everything so tiny that you cannot really see the difference between gold and link LLD. And if you are still using BFD linker, you might, because it's still, I think, user being LD in most systems, then please use LLD, or at least gold, because BFD linker is very slow at compiling large programs. So, well, but every benchmark comes with some footnote, right? And if you read that footnote carefully, then these numbers are measured on a very powerful machine, BH machine. And LLD might be actually faster on these machines, but does that mean that LLD is only faster on such a powerful machine? So this is a pretty legitimate question, I think. And the answer is no, because both gold and LLD has option to disable multi-threading. And so if you give that option, then you can compare bare single-threaded performance. And then if you, and with that condition, LLD is still 2 times faster than gold, as you can see. So there is something fundamentally faster in LLD. So what makes the difference? Well, I don't actually know, because LLD is written from scratch, and honestly, if it's not an incremental update, then you cannot really point out some things that really makes a difference, right? But I can still give you some insight and the ideas that I designed this program to make things faster. And if you try to optimize something, the first thing you have to do is to not optimize it, ironically, because you don't really want to mess up the entire source code base with some premature optimization. But instead, you just want to make something that's naturally faster, right? And I think these figures give you the insight of the scale of the problem we are handling. So in order to link the Chrome with debug info, which is 2 GB in size, by the way, then LLD has to read 70,000 files, 1.8 million sections, 6.3 million symbols, and 30 million relocations. So all these numbers are big numbers, but they are pretty different in order of magnitude, right? So you can spend a lot of time for each file, for example, but you really have to be pretty quick at handling symbols and relocations. Otherwise, your linker is going to be slow. And relocations is actually, despite its number, not that quite bad in terms of speed, because relocation record is a pretty small record in a file, which is consecutive in memory, and you can just read it and do whatever you need to. But symbols are big data, because it's variable in size, and the linker has to do a lot of things for symbols, naturally. And so symbols is going to be the thing that you will focus. So if you spend, for example, 1 microsecond for each symbol, and if you have 6 million symbols, then total amount of time you would spend is 6 seconds, because 1 micro times 1 million is 1, right? So what can you do, for example, in one microsecond? This is so actually you cannot do a lot of things in one microsecond. So for example, you can read only 80 symbols from object files in 1 microsecond, mainly because so symbol table is just a run of now terminated strings in object file. So it doesn't have a length field. So you have to run strlen to get the size of a string to instantiate that data as a string object, and which takes time. And if you insert strings into symbol table, or actually it's a hash table, then you can do that only 4 times in 1 microsecond. So it's so it's not a lot, right? And the situation is so C++ is the one reason why symbol insertion is costly, because of name wrangling. So C++ adds types and namespaces and so on, and gotcha to symbols. And it makes mangled symbols as a string pretty long. And I think that is the reason why we cannot do a lot of things in a short period of time. And I'm not going into the details of the design of LLD, but we have a rule in LLD that we do only one symbol table lookup for a symbol read from an object. So we never do 2 symbol table lookups for the same string. And this really saves time, because I think this is the shortest, smallest number of hash table insertion you can think. And I think this is the reason, one of the reasons why LLD's symbol resolution is much faster than other linkers. And other things you can think of is to use more cores. So my workstation has 20 cores, and even my phone has 4 cores or even 8 cores. So you naturally want to utilize more than 1 core to shorten the latency to deliver results to the user who are waiting in front of the terminal to finish linking. But again, you don't really want to optimize that hard, because debugging concurrency bug is really hard, and it is too easy to mess up the entire design with bad threading design. So you just really want to extract a small amount, small part of the code which can be parameterized and do it. And one thing you have to be careful when doing multi-threading optimization with linker, for the linker is to make it deterministic. So it has to create the exact same executable bit by bit, as long as you give the same set of command line options and the same set of input files. And we have to guarantee that, constraint even with multi-threading. So, so it shouldn't depend on the, for example, number of cores on your machine, or whether it's the thread is executable, threading is enabled or not. So, well, which part of the linker takes time? So this is a breakdown of execution time. So green part, as you can see, like something like 90% of execution time is dominated by only 3 factors. And green part is a time to copy data from input object files to the output file and apply relocations. And yellow part indicates the time to merge constant strings. So object files can contain multiple read-only strings, and the linker can and should merge constant strings so that the generated executable doesn't contain duplicate strings, in order to save space. And the red part indicates the time to read object files and insert symbols into symbol table. So which part can be parallelized? So symbol resolution is somewhat serialized process because the order how symbols are resolved really matter, and you cannot really swap it. So it is hard to use threading for symbol resolution. But besides that, you can actually parallelize it. And if you apply that factor to the Amdahl's law, then you can get this theoretical limit. This is not a real number, but if you have an infinite number of CPUs, and if there is 0 overhead of using threads, then in theory, you can get this number, right? How can we get close to this? So using thread, it's not so there is no single recipe to use threads. So you have to come up with a design to use threading for each different issues. And the copying data from input object files to output file is actually pretty easy to parallelize, because once you set the file offset for each data, then you can just copy it and apply relocations in place, which is in fact just an M-mapped region of memory. And that's pretty independent. So a lot of threads can work on multiple object files and input sections to copy independently and apply relocations independently. And this is pretty easy to understand, and there is no coordination is needed. So merging string is a little bit trickier than that. And this is how we used to merge strings. So this is a very simple algorithm, as you can see. So we just have a hash table, and we insert all read-only strings into that hash table to unify them, right? And how can we parallelize this? And your solution has to create a deterministic output. So it is much easier if your output doesn't have to be deterministic, but just to be correct. But in order to be deterministic, that's tricky. And eventually we came up with design. So now we have multiple hash tables. And for each hash table, we have thread. And each thread picks up strings from string pool and inserts them into their own hash table. And since each thread has its own shard of hash table, it doesn't need any locking, for example, and it doesn't need any coordination between threads. And after all threads finish their job, then we combine all the shards into one. So what is the result of these optimizations? So after optimizing, after applying these techniques, LD takes 1/3 of time than before, which is, I think, a pretty good number. And this is, I think, pretty close to the theoretical limit that we can achieve. So this design is good because still most part of the linker is single-threaded, right? And only in a small part of the code is parallelized. So you don't care about threading or threading bugs when you are dealing with most part of the linker. And this is pretty easy to understand and easy to read. So I said that the LD is significantly simpler than GNU linkers, and we do not really have a good metric on counting, measuring how simple a program is. And I wrote yada yada on this slide, but it basically says that, well, still counting the number of lines can be at least give you an insight how about the complexity of the program. And here's the chart. So if you compare just the linkers number of lines of the two linkers, LD is something around 1/7 in size in terms of number of lines. And this is not really an apple-to-apple comparison because Gold supports more targets. And LD uses libraries to read object files and debug info. But even if you add the number of lines for the number of lines of the library, then LD is still much smaller. And these libraries doesn't include not only ELF, but also have COFF and other parts of the thing. So I think you can still see the difference. And previously I said that you don't really care about the correctness, or you don't really care about anything other than speed when you are talking about the linker. But I think it is not actually true because sometimes linker has to interact with users, right? In particular, when printing out an error message to report missing symbols or duplicate symbols. And Clang did an excellent job on improving C++ diagnostics, right? So before Clang coming to the market, in C++, error messages are very cryptic, and you have to decrypt to understand what's wrong with your program. But so I wanted to do something like that for the linker. So LD's error message uses color, of course, and it uses more vertical space, and it shows error messages in a more structured way, so that it's easier to read. So this is one example. If you have an undefined symbol in your program, then LD prints out error messages like this. And I think that it's easier to read than Gold. And this is another example. So if you have a duplicate symbol, then LD prints out error messages in this way rather than GNU style. And LD includes all the information that the linkers know about the symbols. So it doesn't only include symbol names, but it also includes file names, line numbers, object file name, and if that object file is in an archive, then archive file is printed as well. So GNU, even GNU BFD linker and Gold linker are not really fully compatible in terms of, because there are a lot of edge cases that you can see the difference. And LLD is of course different, but I think that the biggest difference in semantics and behavior in LLD you can find compared to Gold is this. So, and this is about how linkers resolve archive symbols. And in order to understand that, you have to understand how the traditional Unix linker works. So basically, in traditional Unix linker work, visit object file and the archive file from left to right in the same order as they are given to the via the command line. And visiting and reading object file may add may resolve undefined symbols, but it also may add new undefined symbols. And when the linker visits archive file, then it pulls out as many object files as the linker can to resolve as many undefined symbols. And then it goes to the next file. And if you think about that, this scheme results in a picky behavior of the order of the file. So you basically have to give object file before archive file. Because if you do that in a reverse order, then when the linker visits the archive file, then it doesn't pull out any object file because it doesn't have any undefined symbol, right? And then it goes to the next file, which happens to be object file. Then it has an undefined symbol. And then if that's the end of the command line, then the linker reports an undefined symbol error, even though they theoretically can create executable out of the given files. So LLD implements a different semantics, and which is actually Windows semantics. And I like this semantics. So LLD doesn't really care about the order of archive files. Well, sort of care, but it's not very picky. Because LLD doesn't forget archive file symbols after visiting them. So LLD can go back and pull out object files if it has to. And I think this is a cleaner solution and it's more efficient. And you don't really have to worry too much about it because almost all programs just link fine. And in a few cases, you can observe the difference, but in most cases, that indicates an error of your program, like 2 archive files contain the same symbol or something like that. But this is something you want to keep in mind. LLD is one of LLVM umbrella projects. So naturally, we want to be a member of family. So LLD supports link time optimization without plugin. So unlike Gold, you don't really have to do anything to do LLT. Basically, all you have to do is to pass FLTO to Clang and use LLD as a linker. And then LLD takes care of the rest. Also, one thing I want to mention is that so a lot of people are interested in using LLD for cross-linking. And I think that LLD is friendly to cross-linking because of the 2 reasons. First of all, LLD doesn't have any compile time options to disable or enable targets. So as long as you have an executable of LLD, then it can handle all the file formats and all the targets, however it is built. And I think this is pretty friendly to cross-linking. And the other interesting fact is that LLD doesn't depend on host default configuration. So GNU linkers, for example, have default implicit options like default search path for library, and which depends on the operating system. And LLD doesn't have one. but that is fine because we actually have the same configuration in the compiler, and the compilers explicitly pass all the parameters that the linker needs. So in most cases, we do not actually use these implicit options. So we just removed it, or we haven't added in the first place, and it just worked fine. And I think this makes LLD friendly to cross-linking because there is no hidden variable in linker. So basically, this is my talk. So so LLD executable is already included in the binary distribution of the LLVM, so you can just download it and use it. Or if you want to build it, then you can just follow the instructions on the website. Yes, yeah, that's it. So any questions?
Hi, thanks so much for your talk and your work on LLD. I'm very excited in particular for the use of LLD to link the Linux kernel. So I was curious about your slide with the micro benchmarks. I know you said you don't have too much insights, but I was curious, like I was surprised personally that LLD could link the Linux, that all linkers across the board could link the kernel much faster than some of these other, like web browsers, for instance. I was curious if you have any insight about that, and then why BFD might be faster than LLD for the case of the Linux kernel.
It's not BFD, but Gold.
Oh, sorry, okay. And then did that result in kernel boot? Did you try to boot it?
That's a good question. And that's probably no.
Okay.
It was yes at some point of time before, but I'm not sure if that's still true. So yeah, at least at some point, we successfully linked Linux kernel and boots up at least middle of the boot process. And I didn't personally try that, but some contributors tried that, and then he made a good progress. So there is no limitation or fundamental reason that the LLD is not able to Linux kernel. It is more like just because no one is really working hard on that topic. And FreeBSD kernel just links fine and boots fine because that's a system linker. So, well, it's just a matter of amount of effort that we have to make. And the reason why LLD is behind the Gold is that I don't really know the answer. But I guess that the LLD's linker script support is not very optimized yet. So I guess that's why we are seeing the difference.
And then any insights about the kernel relative to browsers?
In terms of link speed?
Yes.
It can be as fast as, I don't, well, if you use linker scripts, then there is some fundamental limitation on the speed. For example, you can use globe pattern to match against a file name. And because it's a string processing you have to do for each file name or even each for symbol, that really takes time because it's more like just a regular expression that you can use. And that takes more time. But I think LLD can be at least as fast as Gold. There shouldn't be no reason not to achieve that goal.
Thank you.
There's a question from guys. If you have a question sitting here, just raise your hand. And guys sitting there, just use microphone.
Okay, thank you very much for your talk, and I'm very pleased to see how much LLDs come on. I tend to work mostly with toolchains for deeply embedded systems, and users there tend to go completely berserk with linker scripts. How hard have you actually sort of exercised the linker script compatibility to check that it?
That's a good question, and we don't really have. So we of course have unit tests for every feature that we have implemented, but I don't know any comprehensive test suite that you can use to measure the compatibility of linker script. So I don't know.
I mean, for example, I think there is a regression test suite with GNU-LD. Have you tried running that?
Not really.
Okay.
How far along would you say the Mach-O support is?
I'm not really an expert in that area because I'm not the owner of the Mach-O port of LLD. So maybe it should be addressed by Apple guys.
A question here.
So I know you said the speed is the important thing, but I've seen more than one case where the linker actually failed because it ran out of memory because it was trying to link something that was really huge. Have you measured the memory consumption of LLD compared to the others?
No, it's on my plate, but I haven't measured that. And if you run PS or something to see the memory usage of LLD, you would see a big number. But that's not really a memory consumption of LLD because LLD uses mmap IO for every operation. So it maps all input files into memory and it maps the entire output file into the memory. But it shouldn't be counted as a memory consumption of the linker. And I guess that because of that reason, we don't really have intermediate data which we copied out of input file. And which means that I think that the LLD uses less memory, but it's not proved.
Any other questions? We still have 2 minutes before lunch. Okay, thank you, Roy.
Thank you.